Bum, 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 ba-na-na-na-na, Biot-Savart. Okay, so this video is going to be a little longer than normal, but what I'd like to show you here is how using Biot-Savart's law, we can get ourselves into saying that for like a near infinitely long wire, the B field is mu naught I over 2 pi r, and if we have like a circular loop of wire, the B field vectors are equal to mu naught I phi over 4 pi r. Okay, so this is kind of setting that up. How do we do that with Biot-Savart? Where do we get these ideas from? Okay. Now, one of the things that we'll need to do is, if you recall earlier when we were talking about Bio, we set up this equation, and I'm not going to go through how to get this equation because it's its own little derivation in and of itself. But dB, where that's a small piece of a B field, is equal to mu naught over 4 pi multiplied by I times the cross product of dl, so dl cross r hat over r squared. And sometimes you won't see this as r hat, so this just designates like it's in a direction but it doesn't have a value. Sometimes you'll see this as just cross r, so it has a value, and this will be r cubed in the denominator. But what's going to happen is there's going to be an r up here, and it's just going to wipe one of them away anyways. So I like to write it as r hat, as being we need to take a cross product here, but I only need a direction out of it. Okay? And once again, to reiterate, this is because we are going to get a small bit of B field for every small little bit of length of our current carrying wire. Okay? So if I am adding up all of these current carrying wires, or all these little bits of current carrying wire, that will in theory give me a total B field at some point in time later. So if we kind of like doodle this just briefly to the side, here's a long current carrying wire. It's got a current in it. And if I'm looking for a B field out here at some point, well, I can think about like every tiny little segment dl out here is contributing to that B field. And this is kind of hard to think about because this dl here, it's not perpendicular to that point. This dl out here is actually, pointing kind of at some weird angle, right? But there is a component to that is pointing perpendicular. And that's where this cross product comes into play here, okay? So what we're going to see here is if we kind of set this up, it is some radial distance away dl. This here is actually some capital R. It is physically how far away from the wire is that point. And then we're going to call this edge down here, we're going to call this some amount L that we've gone down the wire here. Okay, so we're going to come back to that picture in a little bit, but we can imagine that there are a large number of dLs throughout this wire, and we're going to sum all of them up to get some total length. Okay, so to do this, we first recognize that this is a cross product up here, and when we run that cross product, what we're going to get out of this, so we've got mu naught over 4 pi, the current is what it is, and because we don't care about the magnitude of that r, it's just going to give us the cross product here. What we're going to have is a dl, and then there's not going to be an r term out of that. What we're going to have out of it is a sine of theta term, because we've already canceled the r's out, as I showed with that cube before. Okay, and this is all going to be divided by r squared. So what's going on here? How can we get this back to this original equation? Like, how do I get to this ending? Well, if I'm adding up all of these little dl terms, and I'm adding an infinite amount of them, then what I need to do is I need to take an integral. Okay, now when I go and set up this integral here, my integral is going to technically be from negative infinity to positive infinity, okay, because this is an infinitely long wire. Now, if you know a little bit about calculus, you might look at this and go like, oh, well, you're going to have an issue here. This is this is an integral where I can't go from negative infinity to infinity. I need to switch this. So what we're actually going to do is we're not going to bound ourselves from negative infinity to infinity. We're going to bind ourselves from 0 to infinity. And then we're going to multiply by 2 out in front, because we can think about 0 to infinity as being the same as going from 0 to negative infinity. We've just kind of doubled up. So we're going to put this 2 out in front, so it's mu naught over 4 pi. We see the 2 over 4 is going to make things a little nicer here, so we get a 2 underneath as they divide out, which now we start seeing the beginning of this equation. Okay, and then on the inside of our integral, well, we're also going to be able to pull out a current. That current's a constant, so we can pull the current out. So on the inside of our integral now, all we are going to have is a dl and a sine theta. So we've got sine theta, we've got dl, and this is over r squared. Now, how do we go about solving this? Well, let's actually take a look for a second as to what this little r value here is, because this is going to be a big thing for us. If we take a look at this, this is the little r value we're talking about. And since this is a right triangle, we actually know that the r value here is equal to the square root of big R squared plus, and in this case this would be like L squared. Okay? That's a Pythagorean theorem in order to find that there. We also know that when we take a look at the angles here, you know, this is some angle that's sitting out here like this. We know that even though that angle is rather large, we know that the sine of some angle theta is equal to the sine of some pi minus that angle theta. Okay? What this will actually allow us to do here is it will allow us to say that this could be equal in terms of what's going on here. If we take a look at, if this is some angle theta, we can take a look at this and rewrite the sine of angle term as being r over the square root of r squared plus L squared. Okay? So what we did is we basically said like sine is an opposite over a hypotenuse, right? Our opposite, so even though I only have this angle on the outside, it is technically equal in terms of sine to the angle on the inside. Okay, that's kind of this right here. And if that's the case, it is equal to a opposite r over a hypotenuse. Okay, so we just applied some sine rules there to kind of get things in a weird looking way, but it really is just sine is opposite over hypotenuse. Okay, if we take this, which is sine of theta, and we dump it back into this equation here, we can actually write the following. And this is kind of a weird thing to write because it's going to work itself down. We have a sine of theta term, and we've got this r squared term here. So if we actually write this out, what we're going to have is, this is looking so weird already. It's going to be r over the square root of r squared plus L squared dl over the squared of the square root of r squared plus L squared. So over r squared plus L squared. And sometimes I like to actually write these as fractional exponents like that, like 2 over 2. It's just going to be 1. And the reason why I like to do that is if I do the same thing above it when I took the square root, this is like to the 1/2 power. Well, when I look at this and I combine all my terms together here, what I'm actually going to have is the integral with all of my constants out in front from 0 to infinity of r over r squared plus L squared to the 3/2 power dl. Okay? Now, this is a really weird integral, and if you are looking at this and you're like, oh, can I integrate that? Yeah, you can. It is not fun. That's what you'd say if you had to integrate this. I'm actually going to put a link in the description of this video that will take you to another YouTube channel. It's called like Integrals or something like that, or Integrals for You. They work out what this integral is. What I did is I picked up a copy of Schwamm's Outlines Mathematical Handbook of Formulas and Tables. And in here, I just looked it up. And it's actually formula 17.9.15. Or, if you wanted to, you could go to Wolfram Alpha and type this integral in, and it will give it to you. Okay? But it is a pain in the butt integral. It is much easier to look this up on a table. What we'll actually find after we take this magic special integral here is we will get ourselves the following equation. We're going to find ourselves in a situation where we're going to have our mu naught I over 2 pi, because those were our constants there. And then we're actually going to have 1 over r times the quantity of L over r squared plus L squared to the 1/2. And this is bounded by positive infinity and 0. And what we actually find whenever we put values in for this, and you got to do some more mathematics because you're going to have like infinities over infinities here and it's kind of a mess, is we actually find here that this will all kind of zero out. If you kind of know how to do L'Hopital's rules or what you're doing there, what you'll see is you're going to have a infinity over a infinite quantity here, and it's going to actually zero out. And then when we put the 0 in, well, it's going to kind of like, it's going to bring itself out to 1, okay, if you L'Hopital that. So you're going to get a 1 there, and when you put the 0 in, you're going to get a 0, and what you're going to find is you're going to have mu naught I over 2 pi r, okay, and that's going to be your final solution to this, which is what we have up top, okay. It's not a fun thing to derive on the fly, so really I recommend that you just know this equation, okay, just know that for a very, very long wire, mu naught I over 2 pi r, boom, you're good. But how the heck do we get this? What the heck is that? Well, remember, this is for a wire loop. So let's take a look at how we'd run this for a loop. If we take a look at a loop here, we still have the same equation that the individual B fields are equal to mu naught over 4 pi, and then this is I dl cross r hat, over r squared. And as we saw previously, what's going to happen is we're going to get mu naught over 4 pi times I, and we take this cross product here. Well, if we have a wire loop and we're going around it with a current, we are always, for each tiny piece of dl, we are always perpendicular to the center there, which means that, thank you school, thank you, which means that our sine of theta that we got out of this is always going to be 90. So dl cross r in this case is actually just going to be dl, okay, because it's going to be a dl sine of theta term, and that sine of theta is always 90. And then we're just going to divide that by r squared. Now, the real question is, what is dl here? Well, if I were to integrate it all the way around the circle, if I call this 0 and then coming back to it is length L, that would be some length L there, right? Well, how can I actually get that value? Because isn't it kind of dependent on the radius of the circle? If I have a small circle, it's a small amount of size. If I have a big circle, it's a much larger amount of size. And what if I don't even have a full circle? Well, here's how we can think about this. We know that dl is this length of a circle. And if you wanted to get the entire perimeter of a circle, like the entire circle length, we know that's just 2 pi r, right? Well, this right here is some angle measurement. If you wanted like half of a circle, that would just be pi r, where this is still that angle measurement in radian. Which means that if you just want a tiny sliver of a circle, some dl, you just want a tiny sliver of the circle angle, d theta, multiplied by r. We're going to take this and plug it up into here. By doing this, we once again get the mu naught I over 4 pi. When we integrate, we're integrating from 0 to some angle theta. We're going to call it angle phi in this case, simply because that's what physics likes to use here, okay, for this specific equation. So what we have is we have r d phi, which is like the angle, over r squared. And what's cool about this is the r and r squared are going to divide out. This r is a constant, so we're actually going to pull it to the outside. And when we have this, our final integral is going to be mu naught I over 4 pi r, the constant, times the integral from 0 to phi of d phi, which may be the easiest integral we do all year. And we finally see that the B field of a wire loop is just mu naught I phi over 4 pi r. And luckily, that is what we saw all the way back up here in the beginning and what we talked about in class. So these are possible to derive if you have to. The loop is actually much easier than doing a straight line. because of this insane integral, which I told you I'd put a link down at the bottom of this description. But this is just a way that we get those two equations from Biot-Savart, okay? Kind of weird thinking about it, but that's what's going on. We're taking small segments of wire, and then we're adding up all the B fields that these small segments contribute. And that will give us those final B field equations, which we can use for a whole lot of stuff, okay? We're actually going to see later on that getting this equation and this first derivative, or this first integral we did up here, all of that stuff, there is a much easier way to do it, but we're going to have to get into Ampere's law before we know that. But for right now, we are finished. So adios, everybody, and take it easy.